Hello, welcome to the video for 1.13, 114. I'm Coach Weidenbauer, and this is for AP Pre-Calculus. So we're going to combine 113, 114 together here. It's very calculator heavy. I do apologize ahead of time if this is a long video, but I'll be flicking back and forth, as you can see, between my two screens here. We have a calculator and where the notes are. So real quick, just familiarize yourself and just have this sheet of paper here as a reference in your notes on how to build regressions. So that's what we're doing today. It's very calculator heavy. The level of difficulty is low, but the technology that's required is high. So in other words, my parents would struggle heavily because they don't know how to use technology. So I'm going to kind of talk through all this stuff as well. So I'm going to get off of this screen, but we're going to work a little bit on modeling functions and applications here. So our first problem here, we're going to be talking about some babies. Let's do it. Okay, so example one, the age in weeks and weight in kilograms of 5 randomly selected babies from a particular pediatrician's office are listed in the table above. The linear regression of y equals a plus bx can be used to model this data, where y is the predicted weight of the baby and that is x weeks old. Okay, so we're going to write an equation to model this data. So what you need to do is you need to get out your calculator and make sure that you clear it. Okay, so we have a cleared calculator. We're good to go. We're going to be using a stats button. It's going to be right here and below the delete button. We're going to do stats and then edit. And what we're going to do is we're going to use that table that we had from our notes and we're going to plug in. So for the inputs, which is the T, which is the weeks, we'll put that in L1. We'll put the outputs into L2 and we'll be good to go. So type in the 4 and then you got to hit enter. And then 5 and enter, and 6 and enter, 8, enter, and 12 and enter. And then you're going to go over to L2 and just make sure everything corresponds. 4.2, make sure you hit enter between every single one. 4.4. All right, I'll stop talking because y'all can read, right? All right, there you go. So everything's in there that you need. Now, what we're going to be doing is we want to write a regression. So we're going to hit second quit. And how to do that, everything we do today is in that stat button. So hit stat, and then we're going to do calc. And you got lots of choices here. We're going to be focusing on linear regression, quadratic regression, and cubic regression. Now, please take note that they wanted to do the linear regression A plus BX. That's what they wanted. So I'm going to use the one that says A plus BX, which is option 8. There are two linear regressions. They are essentially the same thing. I'm just going to use the one that says A plus BX. Okay. And I'm going to hit enter. And then on my fancy calculator here, it really asks me a bunch of questions. All I'm going to do here is make sure that the X list, which is input, is L1. Well, the Y list, which is output, is Y2. Frequent list, we're going to ignore that. Store, I do want to store this. And if you remember how to pull up the Y1, I want to store this in Y1. So I'm going to hit, the alpha button, F4, and hit enter. And it will automatically take my equation and it will store it in Y1 for me so that I can use it for the rest of the problem. Okay, so it gives me my A value, it gives me my B value. And then so let's go ahead and write this down now. So in my notes, so it's the equation of the linear model. So from my calculator, I had y equals 3.545 plus 0.185. And then I'm using T because that is the input value they want. Okay, so y is actually going to be W of t. So that's our linear regression model. Okay, so now what's really neat about this, since I stored this in y1, if I hit the y equals, it's already there for me. I don't need to do any copying down. May seem like it's not a big deal, but when we get some numbers that are like 10 digits long, we would really, really appreciate having this ability to do that. So that's totally awesome. And here we go. So the first question that we get here is predicted weight when the baby is 10 weeks old. So I'm going to pull up the y1 and plug in a 10. That's the easiest way to do this one. So that baby that's 10 weeks old is going to be about 5.395 kilograms. So we'll do W of 10 equals, and this is our predicted weight, 5.395 kilograms. It's not the only way to do that. If you were to go to the table and graph it, that window looks whacked out. Let's do zoom 6 for regular window. If you hit the trace button, by the way, you can kind of go wherever. If you hit the trace button and then hit the number 10, see how it does like x equals 10? It'll just bring you right to 10. So that's another way to do it as well. Let's look at our next question here. The weight of a 6 baby is 5.3 kilograms. Use the model in A. What's the age of this baby? So now I'm giving you the y values. So I'm going to go to y equals, and I'm going to type in the y value of 5.3. Okay. And it's going to graph a horizontal line. So let me kind of write down what's going on here for this one. So I know W of t here equals 3.545 plus 0.185t. And I want this to equal 5.3. Now, this is one we could just solve this in a calculator totally fine. But just because I want to show you, we're going to type this into y1. We're going to type this into y2. And we are going to intersect to solve for this one. What I mean by intersect, well, make sure that my blue line and my red line intersects. Otherwise, I need to make my window bigger. It looks like it intersects right there. If you're ever curious how to make your window bigger, you just hit the window button. And if 10 is not a big enough number, you can always go up to 20 and graph it and kind of see I have a little room for the intersection there. So the intersecting, it'll open up this blue calc button right where it traces. So second trace, and then choose 5, which is intersect. It's answer the 3 questions. It's going to tell you what's the first curve, what's the second curve, and what's the approximate intersection. So I'm just going to go where the intersection is. It intersects one time, so it doesn't matter where we are with our cursor. So hit enter for first curve, which is blue. Second curve is red. Guess, just hit enter. It's going to give me an answer of 9.4864. So that is our prediction here. So t equals 9.84. Oh, 9. I can't even read my own writing. 9.48. 9.486. And this is going to be weeks old. Okay. So that's us using a linear regression, and we can answer all these questions right here. It's going to take lots and lots of practice just to get used to this. Okay. So let's get into, hey, what models do I use? So selecting appropriate models. So linear models, and this is not new information for us, but linear models have constant rates of change. Quadratic models have linear rates of change. Have linear rates of change. And also, this one's really important too for this, that we are symmetric. So they're symmetric with a single maximum or minimum with context. Okay. And they also involve area too. And cubic is just going to involve volume. So as we read through these or look at tables, we have to guess which model to use. We're thinking about this. If we're constant rates of change, it's linear. If our rates of change are roughly linear, there's our rate of change is constant. Or we have like a symmetric, which is like one max or one min. We're going to use a quadratic. When in doubt, it's probably quadratic really. And then cubic models are going to involve volume. So let's go through this. All we're going to do is just read. We're not doing anything beyond reading and selecting which one of these 3 we're using, linear, quadratic, or cubic. So for example 2 here, balloons are filled with water in preparation for an epic water balloon battle. Each water balloon is roughly spherical. The radius of each water balloon is measured relative to the amount of water that it holds. So this one right here, if we're looking through it, this one is going to be a cubic because we're talking about water being held. So this one would be a cubic because of volume. Next one, Totino's pizzas are on sale at a local grocery store. The price of the one pizza varies between $1.99 to $2.19, varying on variety. The number of Totino's pizzas are counted relative to the price of purchase. So this one is going to be, what do you think? This one is going to be linear. Okay, now that is written so terribly. I apologize. This one's linear. Okay, this one's linear because we have a constant price on toppings. So it's talking about the toppings matter. So we're going to have a constant slope. Because that's the price per topping. Okay. I wonder what the last one is. Just, the sprinkler is placed in the yard to water the grass. Water rotates at a circular pattern and waters all the grass between the sprinkler head and the furthest distance it reaches. The radius of the circular path is measured relative to the area. That's key right there. Area watered by the sprinkler. So this one's going to be quadratic. Because we're talking about area. Okay, so 3 problems. Which one does he use? That can be a hard part. Okay, once you get that part down, all you do is just do everything that we showed you before in the calculator. All right, let's go on to this example right here. So we have a table which provides data for 8 ordered pairs. This is not a problem where we really have an idea of if this is area or volume or what's going on. We just have values. Which function type best models the data in the table? Is it linear, quadratic, or cubic? And then we're going to explain, and then we'll kind of go from there. And we'll just get the equation for the regression model. So if I'm looking at this, I'm looking for constant rates of change for linear. Are there constant rates of change? It looks like we're going up by like 5 and then like up another 5. Okay, so maybe it's linear, but then we're going up by like 2 and then like by 1. So I'm going to say it's not linear because our rate of change is not constant. Okay. Now it's between quadratic and cubic, and I said already it's not a context problem, so it's probably not going to be cubic because we're going to need more information for that. So this one is going to be quadratic. Here's the reason is because we do have a bit of symmetry here somewhere in here. You notice how there's a maximum, how it goes like increases. The numbers are increasing, then they start to decrease. That's going to be quadratic for us. So that's what we're going to explain. So we're going to go quadratic. Quadratic y because y values increase then increase. So y values increase and decrease somewhat symmetrically. I'll just write that. Somewhat symmetrically. So since we're just given data, random data, we can't say it's perfectly symmetric because maybe it's quadratic is going to be. But since we don't have every little piece of data, we can't say exactly. It looks like it's kind of sort of symmetric because we're starting to increase by 5 and then increase by just less than 5, then by like a little over 2, and then by about 1, and then we're decreasing by a little over 1, but that space between is a little bit larger. Just go with this. All right, so let's go ahead and write the equation for the regression model using a table. So we're going to go back to our handy dandy calculator. All right, second quit. I'm going to clear everything that's on the screen. We're going to go to Stat, Edit, and we have this new list to edit. So if you go up to L2 and hit the clear button, hit down, everything clears. So I'm going to go to L1, hit the clear button, press down, everything clears. I'm going to start to type in all of this information now. So I'm going to get 0, 0.4, 0.9. I'll stop saying all the numbers. You get the idea. Okay, so I add all the X's. I'm going to do all the Y's now. And 2.8 at the end. There we go. Oh, nope, 2.8. Okay, hopefully I typed everything in right. I do have a keyed notes next to me, so in case I typed anything wrong in whatever the information I'm giving you is going to be correct. So hopefully I typed everything in right. So second quit. Let's pull up this model. We said it was quadratic, so hit stat, go over to calc, down to quadreg. And it's going to pull from list 1, list 2. Perfect. I do want to store this. Just get used to always storing it. Hit calculate. And then bam, hopefully that matches what I have. It is what I have. Okay, so in pre-calculus, we only need to round to the nearest thousandths. So that is the first 3 digits. We can always round or truncate at that point. So like for instance, for C, our third digit is a 5. We can round it up to a 6 or we can keep it a 5. It doesn't matter. So, and also please take note that this is already in Y1. Oh, clear out the Y2. That's in Y1. Something else too is I can go ahead and graph this. Let's see what it looks like on my current graph. I'm going to change my window up a little bit because I'm from my table is from like -1 to almost 4. My values are from Y is 0 up to like, I'll just go up to 25. So there's my graph. Okay, I can know it's accurate because if I actually plot the stat points, if you go up here and highlight plot 1, it'll actually plot the points for us, and they all go through those points really, really nicely. So I just wanted to show you that. Oh, let me pull this information back up so I have it. Okay. So I'm going to go ahead and copy this down over into my keyed notes so we can see everything. So what is the equation of the regression model? Well, I know my A value was -4.883. My B value was 15.968. And my C value is 4.99. I said you can round or truncate. I tend to just truncate. It's easier for me. So since those are the values, here's my quadratic. Y equals -4.883 x squared plus 15.9. I'm just throwing this in parentheses so you can kind of see it maybe better visually. X plus 4.995. Okay. So that matches that right there. Also, by the way, r squared, just to talk about real quick, the closer the r squared is closer to the 1, the more accurate it is. And that's why, if you notice, it's 0.999999 rounds really up to 1. That's why when I do graph it with everything, it does connect nicely. Okay. I'm going to unhighlight the plot here just so I don't always have it highlighted because that can get a little weird and frustrating. Let's get to the rest of our notes here, talk about some residual values. So whenever we use a model to predict values, or we expect our model to produce reasonably close to the actual values, but our models are not expected to result in the exact values generally. The difference between an actual value and a value predicted by a model is called residual. So residual is the actual minus predicted. Okay, we use some stats verbiage, I guess, or notation there for y minus and the little y with a hat on it. Okay, so we're going to go back to our OG problem for today. Using the model from example 1, okay, what is the residual value of a baby that is 5 weeks old? And interpret your meaning here. So our actual value for a baby that is 5 weeks old is going to be 4.4. Okay. Our predicted value from this, from the first problem, do I even have that? Oh, I would need to type everything in. I kind of cleared everything from my calculator. I guess I should have stored it. But anyway, using this model right here, if I were to plug in a 5, plug in a 5. Let me do that mentally real quick. Oh, plug in a 5. It's clearly 4.7. It's actually right. Actually, that's actually wrong. It's 4.47. Okay, so actual value, predicted value, that's me plugging in. My residual value is going to be the difference between that. So it's going to be actual minus predicted. So the answer is negative 0.07. Okay. What does that interpretation mean? Since our residual value is negative, we had an overestimate. You can look at it and tell we had an overestimate of actual values. All right, so we're going to get more into residuals in just a bit, but that's the basics. That's all we need to know for right now. Do not forget to like and subscribe. Again, I am Coach Mindmower.